In this last lecture, we're going to look at how the universe began, has changed over time, and what might happen to it in the future. The Big Bang Theory is all about the origin of the entire universe, meaning all of space and everything in it. The Big Bang is basically the moment of inception, or the starting of the universe. It happened about 13.8 billion years ago when all of matter and all of space was created. And just a quick note before going any farther, I wanted to mention that in no way does the Big Bang Theory deny the possible existence of God. I know that some of you are probably not religious, while a bunch of you are. The Big Bang does not explain what banged, why it banged, or who, if anyone, made the universe bang in the first place. In fact, the person who came up with the Big Bang Theory was actually a Catholic priest. I'm pretty sure he believed in God, and I think that's pretty much a requirement for being a priest. I just wanted to make sure that you all understand that believing, or at least understanding the theory, whether you believe it or not, does not have any effect on religious beliefs you may have. The theory doesn't actually contradict the existence of God in any way. So now, back to the theory.
Now remember, we've already talked about the nebular theory, which is about the formation of the solar system. See the diagram on the side illustrating the nebular theory. Remember, the solar system started out from this cloud of gas and dust that began to spin and flatten. The early sun, the protostar, began forming in the middle, and then all the planets around the outside. This is the nebular theory that is about the formation of just our solar system. The sun, all the planets, the asteroid belt, the Kuiper belt, the Oort cloud. That is it. Very, very, very different than the Big Bang Theory, which is about the formation of the universe. These are not competing theories. They're explaining completely different things. A lot of times people get them confused and think that they're trying to explain the same thing, but they're not. Now, when we talk about the Big Bang Theory, we're talking about what happened to start the universe. Now, one interesting thing is that the name, the Big Bang Theory, is really a misnomer. It does not describe what really happened. The universe started out from a particle smaller than an atom, so it was definitely not big. But also, since there was no gas or other material to transmit sound waves, there was also no bang. It would have actually been a silent explosion. So what's interesting is that it was really more of a small shh than a big bang. Now, this theory was developed by a Catholic priest named Georges Lemaitre. He did not name it the Big Bang. He described the theory, but the name Big Bang was given to the theory by Fred Hoyle, who was a different astronomer who thought the theory was stupid. Hoyle believed in an alternate theory called steady state, which basically says that even though the universe is expanding, this is an undisputed fact, he still thought that the universe does not change in appearance over time, and it has no beginning and no end, which seems kind of contradictory. If we know that the universe is expanding, how can it not change in appearance? This theory is pretty much totally defunct now. Here's an image, though, that tries to show you the difference between the two theories. The first one, the Big Bang, what we see is a certain set of dots. Imagine that each one of these is a galaxy. Over time, as time moves on, we have the same number of galaxies, they're just getting farther and farther apart. What's different about Hoyle's theory in steady state is that here is this same density of galaxies occurring in the same area. But it just seems like we have random other galaxies on the peripheral edge just popping into existence. Where is that new matter coming from in order for the density of the universe to remain constant? To be honest, it really doesn't make much sense. Anytime you have to explain the magical appearance of new material, it pretty much means you don't understand what's going on.
Now, when we talk about space expanding, it's not really that the material moving outwards is expanding. What's happening is that the space between the objects expands. In this image, you can see from this tiny original point, material has gotten farther and farther apart as the space between it expands. Let's talk about 2 ways to describe that.
One way of describing this that I really like asks you to imagine a lump of dough that is getting ready to be baked. Imagine that this dough has raisins in it. What happens is when we first make the dough, the raisins are distributed in a particular pattern, a certain number of centimeters or inches or whatever apart from one another. But before you bake it, and even during the baking, the bread rises. So the raisins, although they don't change in size, the space between the raisins actually gets larger. The galaxies aren't getting bigger, the stars aren't getting bigger, but the amount of space between them is getting bigger.
In the case of the dough, yeast metabolizing sugar in the dough creates carbon dioxide bubbles that pushes the raisins apart. In the case of clusters of galaxies, we don't fully understand what's actually causing the expansion. We currently call it dark energy, and studying and trying to detect this energy is a major focus of physics and astronomy research today.
Another example asks you to imagine you have a balloon with little stickers pasted on it. As you blow up the balloon, the size of the stickers does not change. The image on the stickers does not change. It's just the amount of space between them that goes from being small to bigger to biggest. This picture shows the entire evolution of the history of time up until the present day. Now, please notice the numbers across the center. This drawing is not to scale. The first second of the universe is taking up almost half the graph from 10 to the power of negative 43 seconds. We have a super fast process called inflation happening, which is basically the universe expanding from a tiny atom-sized piece to something about the size of a grapefruit. Here, at this time, we have no light, just immense heat. We basically have a soup of electrons and quarks, which are the particles that make up protons and neutrons, and other small fundamental particles. We don't actually have atoms yet. At 10 to the negative 6 second, now remember, if you're uncomfortable with these numbers in scientific notation, 10 to the negative 6 means that we're going to take our number 10 and shift the decimal 6 places to the left. So what we have is a very small fraction of a second. We actually have these quarks clumping together to actually form protons and neutrons. So at this point, the universe is not even a second old. We have electrons, protons, and neutrons. But only 3 minutes into the universe, we are still too hot to form atoms. At 10 to the 8th degree Celsius, which would be 10 and then 8 more zeros, so 100 million degrees Celsius, light is still prevented from shining. The universe is still a super hot fog. Now we're going to start looking at things when we can actually see things in our universe. This happens somewhere between about 3 and 400,000 years after the Big Bang. The universe has now cooled to a still hot but much cooler 10,000 degrees Celsius. This is still hotter than the surface of our sun, but it's within the temperature range of many modern stars. At this point, we have protons and neutrons settling in with electrons to actually form our first true atoms, and light can finally shine. So the first, earliest baby picture of our universe we can actually see is from this time, and we'll look at that picture in just a moment. Now, 1 billion years after the formation of the universe with our Big Bang, notice our temperature has actually fallen dramatically, negative 200 degrees Celsius on average. Now remember, an average doesn't mean that everything is that temperature. Obviously, stars are burning very, very, very hotly, but all of the empty space between the stars, between the galaxies, is very, very cold. Very empty space by 15 billion years after the Big Bang. Remember, our entire universe is only considered to be 13.8, 14 billion years old. We haven't even reached 15 billion years yet, but we're pretty close to it. We're very quickly approaching absolute zero. The temperature, that means we have zero molecular movement of atoms. Here, space is almost as cold as it could possibly be. So you may say, okay, we have this theory, but what's the evidence? Why do so many people really believe in the Big Bang? Is it really realistic that everything in the universe started from some tiny speck that exploded? Well, stars, as we know, are made of different elemental gases. And we can see that when we look at their chemical composition through a spectroscope. Remember the lab where you looked at these individual line spectrums? Each of the star's elements produces a specific pattern of these spectral lines that is like a fingerprint. Each spectrum identifies what elements a star is made of, each of these corresponding to a different wavelength. Now, when we look at white light, we see a continuous spectrum that looks like this: red, orange, yellow, green, blue, indigo, violet in shortening wavelengths. But when we look at individual stars, we see a specific pattern of lines that occur depending on which elements we are looking at.
What we see, though, when we look at distant stars is that the patterns of the star's spectrum look the same, but the pattern is slightly shifted. The first scientist who identified this shifting pattern was Edwin Hubble. He's the man for whom the Hubble Space Telescope is named. He observed that distant stars in distant galaxies were considerably redshifted. And let's take a look at what that actually means. We have two possible situations. Take a look at the image at the bottom of the screen. What you see is a specific line spectrum of some star or combination of gases represented by the spectral lines I've marked with a yellow arrow. But can you see that each line has a buddy shifted over slightly to the red side of the spectrum? Spectral lines can shift, though staying in the same pattern. The same spacing exists, but shifts either slightly toward the red left side of the spectrum or slightly toward the blue right side of the spectrum. And depending on which way they're shifting, we can actually tell whether the stars are coming toward us or away from us. If you download the PowerPoint and watch it in slideshow mode, you'll see that this graphic is an animation. One of the sets of lines remains still, while the other set shifts back and forth. The pattern of the lines always stays the same, but the place where the lines exist is slightly different. When lines are shifted toward the blue side of the spectrum, that indicates the light source is coming toward us. If the lines are shifted more toward the red side, that indicates that the light source is moving away from us. Let's take a look at how this works.
This process is called the Doppler effect, and you may have heard of this if you've taken a physics class. When a source of light or sound is moving, the sound or light waves change in frequency. Here we have a picture of a static, non-moving object. But what happens is that when the object starts moving in one direction, there are these waves that get tighter together, shorter wavelengths. But if the object is moving away, that wavelength is actually stretched toward the opposite end of the spectrum. What's interesting, though, is that red and blue shift not only tell us which direction something is moving, but it also tells us the speed at which it is moving away. Let's take a look at this first image, and let's say these two lines had been shifted slightly in this direction. That would tell us that this object is moving away from us, but at a slower pace than this pair that is moving more quickly away from us. In the same manner, had these lines been slightly toward the blue side, they're coming toward us, but not at a very fast pace, as compared to a pair of lines that would be over here, which would indicate that the object's light source or sound source is coming toward us much more rapidly. We actually hear the Doppler effect in normal everyday life. If you've ever had a police car with its siren on, or a horn, or even a train passing by you, what you hear is when it's coming towards you, it's a very high-pitched sound, represented by these waves being very, very close together. A high-pitched whine, like nee. But the difference is, when you're behind that object, as that object passes by you, you notice a very different change in the frequency. The sound goes from high pitch and drops to low pitch. And we can see the same thing with light. So notice in the first image of the stationary source, again, stationary means not moving, there is no shifting that has occurred with these lines. But we see differences in the other two images. When something is approaching us, coming toward us, notice that each of these lines is shifted just a little bit toward the blue side of the spectrum. We call this blue shift. But in the lowest image, when this object is receding, that means traveling away from us, we see that each of those original lines are shifted a little bit toward the right, toward the red end of the spectrum.
So the little rhyme you can use to help you remember the difference is that if the shift is blue, it's coming toward you. For the red shift, remember that R not only starts out the word red, but also the word receding. Just like a receding hairline, receding just means retreating away from you.
We need to know what exactly is happening with the velocity of the light source, like a star or a galaxy, in order to properly study it. Is it approaching us, or is it receding away from us into the distance? So here's a sample question. The diagram lists the spectral lines of hydrogen gas. If you remember the spectroscope lab, we had one line in the red part of the spectrum. We had another line in the green part of the spectrum, and some people could see either a blue or a violet light also in that spectrum. But notice what's happening to galaxy A and how these lines are different from the original set. Then compare both sets of lines to galaxy B, and then finally all three of those sets to galaxy C. Our question asks us, what is the best inference? Meaning, what can we actually tell about all of these galaxies? Well, the first thing that we see is that every set of lines after the first one is shifted in this direction, toward the red end of the spectrum. Now, remember, a red shift indicates that the light source is moving away from us. So number 3 cannot be correct. They are not all moving toward us. Now, it is true that they are all moving away. So we don't have a galaxy moving toward us or 2 galaxies moving toward us. They are all moving away from us. In fact, Galaxy A is moving more slowly away from us. Galaxy B is moving a little bit more rapidly away from us. And Galaxy C is moving the fastest, at the most rapid pace, away from us.
We can tell this because the more each set of lines is shifted, the faster the light source is moving.
Now, what Hubble noticed is that all. Notice this word does not say most. It says all distant galaxies have red shifts. That means all of the very distant galaxies, the farthest away objects that we can see, are traveling away from us. So this is where Lemaitre came up with the idea of the Big Bang Theory. If you were to see an explosion, you would see all of these objects racing away from one another. So if we know that the objects are currently racing away from one another, if we could rewind back time, they would all come back together at a point. We can actually find out at what point they were back together, and remember, that was about 13.8 billion years ago. Now, that's not the only evidence for the Big Bang, although it is some pretty convincing evidence. The next one talks about energy. You've probably heard of one of Einstein's equations, that E is equal to mc squared. E is for energy, and m is for mass. What's happening is that a mass of matter is related to energy in a ratio related to c squared, which is the speed of light squared. Now, what this tells us is that when all of the matter in the universe was created, it was released in a huge amount of energy. And if all of this much matter and this much energy being released, we should be able to see this radiation all over the universe, mixed in with the energy that's being given off by stars. Now, this is what is called the CMB, which stands for the cosmic microwave background radiation. And the reason why it's called that is that it's coming from the background. It's coming from everywhere, all over space. Cosmic just means related to space. Now, the reason why it's called microwave radiation is because it would have started out as light in the visible part of the spectrum, and also heat from the infrared portion of the spectrum. But if you remember your electromagnetic spectrum from a couple of sections ago, the order goes from radio, infrared, visible light, ultraviolet, X-ray, and gamma rays. But what happens is that as these are expanding away from us, they're shifting away from being infrared and visible light more toward the radio portion of the spectrum. And microwaves are a special type of radio waves. This radiation was discovered in 1964 by accident by a couple of radio astronomers called Arno Penzias and Robert Wilson, who won the Nobel Prize for this. If you're interested in learning more about the cosmic microwave background radiation, there's an excellent episode of Through the Wormhole with Morgan Freeman that you can watch that talks a little bit more about Penzias and Wilson's discovery. The episode is titled Before the Big Bang.
The funniest bit about Penzias and Wilson's story, though, is that they discovered this radiation by accident, having found some weird static in their equipment. At first, they thought it was just interference of pigeon poo, as a family of pigeons had taken up residence, making their nest in the telescope. As it turns out, they found evidence of the Big Bang.
Now, this is actually the universe's baby picture. That episode of Through the Wormhole talks about a specific instrument that we have called the WMAP, which has a way of using this radiation that's emanating from everywhere, every direction out in space, to see the distribution of temperatures of objects throughout our entire visible universe. The upper picture is a lower resolution image, meaning more kind of blurry image. And the second picture is a much more clear photo. But what we're seeing here, these little red spots are areas of slightly elevated temperature, whereas the darker blue areas are areas of slightly cooler temperature. But the scale is very narrow. This is showing us that there's actually only a very small distribution of temperatures very, very early on in our early universe. Remember, this is between 300,000 and 400,000 years after the Big Bang. This is the youngest picture of the universe that we will ever have. Another piece of evidence comes from the very recent discovery of gravitational waves. Gravitational waves have been a theory for a long time, but they weren't definitively identified until just a couple of years ago. One of Einstein's theories talks about how large objects literally warp space. This is why planets are able to stay in orbit around stars and how moons are able to stay in orbit around planets. There's what's called a gravity well, a depression in the fabric of space and time that keep things orbiting. What scientists realized was that when we have extremely energetic events like black holes colliding, they should cause ripples through space-time, in much the same way as throwing a rock into a pond creates ripples. We were able to detect these ripples just a couple of years ago, and 3 scientists on the team won the Nobel Prize in Physics. So what's very interesting is that you may have heard the phrase that if you're looking through a telescope, you're looking into the past. That sounds pretty strange, but what this means is if we were to be looking, say, outside at the star Betelgeuse tonight and we saw it explode, that star didn't explode today. It exploded over 640 years ago. It just took light that long to reach us. Remember, we've talked about how light travels at 186,282 miles per second. Alternately, we can write that as 300,000 kilometers per second. Now, even though that's very, very fast, it's not instantaneous. So what that means is if we're looking at something that is 1 billion light years away, that means that the image we see is not what the object looks like today. It means that's what it looked like 1 billion years ago. There's another phrase that we use called redshift to describe this time lapse. The bigger the redshift, the longer ago in history we're seeing the object the way it looked then.
So you may be asking yourself, how do we know that the universe is 13.8 billion years old if humans have only been around for less than 1 million? How do we know? Well, since all galaxies are moving out away from us, all we have to do is calculate how long it's been since all the galaxies were together. And we have some very specific ways of telling how fast these galaxies were traveling at different points in history. There's a short 5-minute video in your Canvas shell right above this lecture that explains the process more fully. You may have heard of Stephen Hawking. He was a famous physicist that you've probably seen on TV. Now, what he said was that an expanding universe does not preclude a creator, but it does place limits on when he might have carried out his job. That's basically a fancy way of saying we don't know whether there's a God or not. Hawking isn't saying there isn't, but it does mean that the universe must have been in existence for this amount of time, whether there was a God or not.
So when we look back in time, we're looking at everything, at how it was back in the past. So if we look at a galaxy that looks like this is pretty near to us. That means that what we're seeing is a pretty recent, a galaxy that's been in existence for a long time. But if you look at this image, though, through the Hubble Deep Field, this is one of the most distant photos we've ever taken. What we see here is a picture where galaxies are much closer together, much more densely packed. This is what the universe looked like when it was very, very young, before it had expanded to its current size. Many people will ask, so, if we know how the universe began, do we know how it will end? Until recently, we weren't really sure, because the answer depends on the density of the universe. If the universe is very, very dense, meaning that the mass of the universe compared to its volume is too big, what would happen is an idea called the Big Crunch. Imagine you have a rubber band that you stretch and stretch and stretch and stretch. Eventually, that's going to snap and come back together. If the universe is very dense, it will collapse back too, like the rubber band. This is called a closed universe. Now, current evidence says that this is very unlikely. We think that the mass of the universe is not big enough for that to happen. The universe, because it's still expanding, and the rate of expanding is actually accelerating, that means that the amount of mass in the universe is being spread over a larger and larger volume. It's becoming less and less dense. So the far more likely event for the fate of our universe is what we call the Big Freeze. This means that objects will continue to get farther and farther apart. And as molecules get farther apart, they collide less, producing less energy, and so the universe will probably end frozen and very thinly spread across space.
Again, this anti-gravitational force is not something we've been able to measure yet, but we call it dark energy, and it's something we will probably know a lot more about in the years to come.